Okay, so now we are going to have a brief discussion of another important family of graphs, or another class of graphs, which is very simple and very fundamental, called the trees. We mentioned it already. We discussed a little bit. Okay, so they call that a tree is a connected graph without cycles. So it's also called connected acyclic. Acyclic means without cycles. All right. The reason we call the tree is because we can draw like a tree. So this one look like a tree. So rows. Sometimes there are special vertex in the tree designated as root of the tree. Sometimes we don't. So here it's not the root of the tree, just a tree and undirected graph. Right. Now, if we do not require connected conditions, then the graph we obtain will be a collection of trees, which of course is called forest. In other words, each connected component of a forest is a tree. So we have a collection of trees. So this one is a forest, of course. It's called a forest. If we have many trees, more than one tree, then it's called a forest. So that's a forest. All right. So that's the definition of a tree. Now, tree has a lot of important properties. So here I listed 5 of them. All of them are equivalent to a tree. So by that, I mean, you can say that T is a tree. So typically for tree, we use T instead of graph because tree starts with T. So typically tree will use this one instead of G equal B. So we use T instead of G for simple reason because tree starts with T. Okay. So all these conditions are equivalent. So by that we mean that you can say T is a tree if only if it is connected and has n-1 edges. Or you can say that combining 4 with 1. So T is a tree if only if T is connected and every edge is a bridge. Okay. So there are at least 5 equivalent conditions with respect to tree. So this one says as far as T is connected and has n-1 edges, then it gives us a tree. The number of edges, n-1, actually will rule out the possibility of a cycle. So it's connected and has n-1 edges. So we don't have enough edges to create a cycle. Therefore, it has no cycle, so it's become a tree. Okay. The third one says the graph is contains no cycle, but the number of edges is n-1. So here, when the graph has no cycle, we have to use n-1 edges to make the whole graph connected. If we have n-1 edges, the whole graph will be connected. So this one is this connected graph with 4 vertices. In order to connect it, least the number of edges I need will be n-1. So if I use 3 edges, I can make them into one piece without creating a cycle. So here, a cyclic condition with n-1 edge will force the graph to be connected. So this one becomes a tree. All right. A fourth one says it's connected, then every edge is a bridge. So every edge is a cut edge. So this every edge is a bridge condition means it will not contain cycle. If we have a cycle, then edges in the cycle cannot be a bridge. If I remove it, the graph is still connected. So it's very important that every edge is a bridge. All right. So connected and every cycle, every edge is a bridge means the graph contains no cycle. So that part actually means it's acyclic. All right. So you can see in this graph, if I remove any edge, the tree will be broken into 2 pieces. So that's what means if I remove edge, tree will be broken into 2 pieces. Any edge, if I remove this edge, it will be 2 pieces. If I this edge, one single vertex and rest. If I add this edge, 3 vertices and rest. All right. So if I remove an edge from tree, the tree will be broken into 2 pieces. And this condition says for any 2 vertices, there is always a unique part in the tree. Again, this one means no cycle. And if this is a path, means the graph is connected. All right. If this is a path, means for every pair means it's connected. But uniqueness, a unique path means no cycle. If there's a cycle, so for these two vertices, I can have a path like this, and path like this. I will have two paths. So for example, this vertex and this vertex, we can find a unique path like this. They are all unique paths. And then the sixth one is equivalent to this one because of this property, unique paths. So if you add an edge to the tree, then unique path together with that edge will create a unique cycle. So if I add an edge between these, so this unique path together with this edge, I get a cycle. So these are very same thing, but stated in a different way. Okay. So for example, if I add say one more edge, let's try one more. So this one, maybe this one. Add this edge, that will create a unique cycle. This cycle. Okay. So all these conditions are equivalent and will be useful when we study trees. Now I want to discuss two fundamental properties about a tree. Okay, we mentioned earlier spanning tree. Given a graph, connected graph, given a connected graph, a spanning tree is just a subgraph that contains all vertices of G. And furthermore, the subgraph itself is a tree. So that's called a spanning tree. So T is a subgraph of G. So means T consists of taking some edges of G. All right. So what we have is whenever G is connected, we can always find a spanning tree. It always contains a spanning tree. The idea actually is very, very simple. Now, a tree has a property that every edge is a cut edge. Okay. So we look at this graph. After pick up an edge. If this edge is not a cut edge, we just throw it away. Because if it's not a cut edge, we throw it away, the graph is still connected. So we keep on throwing edge away. Eventually, what's left are edges that are cut edges for the final graph. So this graph actually is exactly the spanning tree of G. For example, in this graph, okay, so this one is not a cut edge, I can throw it away. The after pick one, this one is cut edge, I cannot. This one not cut edge, I can throw it away. So keep on doing so. So actually in any cycle, we can delete at least one edge. So pick a cycle, delete one edge. So this one is not a cut edge because it belongs to a cycle, we can remove it. So this cycle, remove it. Now, every edge is a cut edge. Every edge becomes so this one. Uh, these edges form a spanning tree. So these edges. Okay. So these edges form a spanning tree. So that's the minimum number of smallest graph that's required to connect all those together. A spanning tree, what the meaning of spanning tree is its minimum smallest graph, smallest subgraph. So in terms of number of edges, that's the smallest subgraph to connect all of these together. If we delete one more edge, then the graph will be disconnected. So that's kind of minimum requirement for connected graph. Okay. So in many applications, we want to connect all vertices together with minimum cost. So what we need is so-called the minimum spanning tree, which we'll be discussing algorithm cost or in data structure cost. I think you may see minimum spanning tree, data structure cost, even in programming cost. Okay, minimum spanning tree. Okay. One more thing about tree is a tree has a special property that a certain number of vertices are leaves. If we look at the tree we seen earlier, you see some special vertices, the vertices of degree 1. So these are vertices of degree 1. So these are called the leaves. Okay, a leaf is called a leaf if its degree is 1. Uh, leaf is useful when we're discussing on a tree because if we delete a leaf, if we delete a leaf, what I get is a smaller tree. So it's quite useful if we use induction to prove something. For example, in the homework, I want you to count the number of leaves. If you allow to use induction, it's very easy to prove it. I delete a leaf, all right? So I get a smaller tree. Then I can use induction hypothesis on the tree. Now for trees, it's easy to see that it contains at least 2 leaves. Every tree always have at least 2 leaves. The extreme case when it has exactly 2 leaves is palm. Palm is a special kind of tree. It has 2 leaves. That's extreme case. For palm, we have exactly 2 leaves. In general, tree have more than 2 leaves. You see, we have a lot of trees. We have a lot of leaves in this tree. Now the reason is degree. As in the homework, again, it's become a hint for homework assignment. One question in the homework assignment. I want you to give a formula for the number of leaves in a tree in terms of degree. All right. So let's take a look. So what degree means, actually it's a branching out. So if degree equals D, that means it's a branching out in D ways. So if degree is D, it's branching out in D ways. So each branching out actually will contain at least a leaf because no cycle. Eventually, so somewhere has to have at least one leaf. All right. So at least one leaf. So that's if degree is 4. So branching out, it will have at least 4 leaves. Yeah. Now, of course, in the middle, somewhere it's this one may branching out again. So if this one degree is also 4. Now it's branching out. So this will one leaf, this will one leaf, but that one will be overcounted when we do this one. So this one, it's counted twice. All right. So therefore, the total number of leaves is not degree sum, but rather degree sum needs to be -2. So how can you get that formula for trees? Okay. Okay. I will not give you further hints for the time being. I will may give you something on Friday. Okay. To tell you more about how you prove that uh, formula in terms of the number of leaves on trees. All right. I think that's good enough. Okay, for trees, you have should have enough for doing homework. All right. Okay. Thank you. That's it.